So let's talk about one of the most important things in mechanical design, how to avoid those huge, costly mistakes. We're going to break down the common traps that can sink a brilliant idea and show you how to get it right from the jump. You know this quote? It absolutely nails it. See, you can model a part 100 different ways, and they might all look right on your screen, but the truth is, only a few of those ways are actually good engineering. It's the difference between just drawing something and designing something that actually works. So you gotta ask yourself, that gorgeous 3D model you've been working on? Is it a masterpiece? Or is it a ticking time bomb, just waiting to blow up in manufacturing when fixes are crazy expensive? To figure that out, we're gonna walk through what I call the 5 deadly sins of design. We'll start with the CAD illusion, navigate the manufacturing minefield, talk about tolerances, assembly nightmares, and wrap it all up with the one philosophy that changes everything. Okay, first up, the CAD illusion. This is huge. It's this belief that because a model looks perfect on the computer, it's going to be perfect in the real world. And this right here is probably the single most common, most expensive assumption an engineer can make. You think, hey, I can draw it so it can be built. You design 2 parts to fit perfectly, with the exact same dimension, because you figure you just send the file to a machine and a perfect part comes out, right? Well, reality is a lot messier than that. And this is what happens when that illusion takes over-engineering. I mean, look at this mousetrap. It's incredibly complex, sure, but is it any better than the classic simple design? Probably not. A simpler design almost always means fewer parts, easier assembly, and way lower costs. Complexity really has to earn its place. All right, let's dive into sin number 2, the manufacturing minefield. This is where your perfect digital design slams headfirst into the physical limits of making stuff. It's all about something we call design for manufacturability, or DFM. You know, the crazy thing is, all this stuff looks totally fine in CAD, but if you're a machinist, these are giant red flags. Sharp internal corners, a round cutting tool can't make a sharp corner. It's physically impossible. Deep, narrow holes, your tool's gonna chatter and break. And using non-standard hole sizes means someone has to buy a custom, expensive drill bit. Every single one of these is a direct hit to your budget. So, how do you fix this? Easy. You have to think like the person who's actually making your part. Go talk to the machinists and do it early. There's this great story about an engineer who specified a super precise 0.427-inch radius. The machinist just called him over, held up 3 tools and said, "I've got an 1/8, a 1/4, and a 1/2 inch. Pick one." Total light bulb moment. You have to design for the tools that actually exist. And look at this. This is it in action. On the left, you've got a machinist's nightmare. On the right, a part that's easy to make. See the changes? The sharp corners now have a radius that a standard tool can handle. The holes are standard sizes. These tiny tweaks don't really change how the part works, but they make it way cheaper and faster to produce. All right, on to our 3rd sin. This is the one that quietly bleeds projects dry. Death by 1,000 tolerances. This is all about how precise a part needs to be. And trust me, getting this wrong is a disaster. It really boils down to this simple trade-off. Go too loose with your tolerances, and your parts won't fit together right. Your product will fail. But if you make them way too tight just for the sake of it, you are burning money for absolutely no good reason. I mean, this chart says everything you need to know. The relationship between how tight your tolerance is and how much it costs isn't a straight line. It's exponential. The more precision you demand, the cost doesn't just go up, it skyrockets. You're suddenly paying for better machines, more skilled people, and a way higher scrap rate. So what's the pro-level move here? It's something called GD&T. Instead of just slapping a plus or minus on everything, which creates a clumsy square tolerance zone, GD&T lets you define tolerances based on how the part actually functions. Think about it. Why use a square zone for a round hole? GD&T lets you create a more logical circular zone. This can actually loosen the tolerance while making the fit better, saving a ton of money. It's all about being smart, not just tight. Okay, let's zoom out a bit for our 4th sin, assembly and service nightmares. A perfect part is totally useless if you can't actually put the thing together or take it apart later to fix it. And this is the kind of stuff that sounds so obvious, right? But it gets missed all the time. Can a wrench even reach that bolt you just put in the model? If you need 3 people and a special jig just to hold things together for 1 screw, that's a bad design. And seriously, please don't use 23 different kinds of screws when just 2 or 3 would have worked fine. So the fix here is all about designing for the entire life cycle of the product. You've got to think about the person on the assembly line. Add little features like pins and tabs that make parts just snap into place. And think about the technician who has to repair this thing 5 years from now. Design and access panels. It's about having respect for everyone who's going to touch your design long after you're done with it. And that brings us to the final piece of the puzzle, which is really more of a mindset than a mistake, the Foresight philosophy. This is what ties it all together. If you take one thing away from all of this, let it be this. Great mechanical design isn't just about being creative. It's about foresight. It's the ability to see into the future, to see the problems coming in manufacturing and assembly and service, and to design them out before they even happen. So, here it is. This is your new design mantra. Think like the person making the part. Remember that simplicity almost always wins. Build and test prototypes early and often. Talk to everyone, machinists, technicians, users. And finally, master your tolerances. Be precise only where it really, truly matters. So I'll leave you with a question. Think about your own work, your own process. Which one of these mistakes are you going to consciously eliminate from your very next design? Because that, right there, is the difference between a good engineer and a truly great one.